Okay, so hi everybody, welcome back. Today in this video, we're going to continue with our Chapter 19 lecture on heat and temperature. And where we left off last time was a discussion of specific heat. So remember, the specific heat of the material is the amount of heat that you would need to add to 1 kilogram of that material in order to get its temperature to increase by 1 degree Celsius. So the next thing we're going to define is latent heat. And to understand what latent heat is, we're going to take a look at some data. So in this graph that you see at the bottom of the page, this shows what happens when we have a sample of water, H2O, which is initially solid and at a temperature of minus 40 degrees Celsius, but we gradually heat it up. Okay, so on this graph, you see the temperature of the water in degrees Celsius on the vertical axis, and then you see the heat that's added to the water on the horizontal axis. So here, let's take a look at the very start of the graph. The initial temperature is minus 40 degrees Celsius, and we haven't added any heat to it yet. So let's see what happens if we start at this point on the graph, and we follow it along going to the right. So we're seeing what happens as we add more and more heat to this sample of ice. So at first, what's happening is if you add some heat, the temperature goes up. And then the more heat you add, the more the temperature goes up. In fact, there's just a linear relationship between the temperature and the heat that's been added to the ice in this region over here. And that trend continues all the way up until the point where we reach 0 degrees Celsius. So there's a linear relationship from the start all the way up until the point where we reach 0 degrees Celsius. And that's the melting point of the ice. But something interesting happens past that. So at this point on the graph, we have solid ice right at the melting point, right at 0 degrees Celsius. If we add more heat to it, past this point, the temperature actually doesn't go up anymore. The temperature just stays constant at 0 degrees Celsius. And what's happening as we add more heat at this temperature is the ice is actually now melting. It's undergoing a phase change. It's turning from solid to liquid. So the more heat we add, the more ice we melt, and that continues happening up until the point where we have completely melted all of the ice, and now it's all liquid water at 0 degrees Celsius right here. So once we've completely melted the sample of ice, if we add more heat, now the temperature can go up again. So we have completely liquid water here, we add more heat, the temperature goes up. Now there's a linear relationship between the temperature and the heat that we add in this region. So the temperature keeps going up as we add more heat. But then once we reach 100 degrees Celsius, something happens again. We're at the boiling point now. And so if we have liquid water right at the boiling point and we add more heat to it, the temperature doesn't keep going up. Instead, what happens is we're actually undergoing a phase change. We're converting that liquid water into steam. And the more heat we add, the more of that water we're converting into steam. So that keeps happening at this constant temperature of 100 degrees Celsius, all the way up until the point where now we have completely vaporized all the water. Now it's all turned into steam. And if we continue to add heat past that point, then the temperature will go up again. Now we have steam whose temperature is increasing as we add more heat. So what we see here is if the material is not undergoing a phase change, like it's all just liquid water in this region as an example, any heat that you add goes to increasing the temperature. But if you are undergoing a phase change, the added heat doesn't go into increasing the temperature. The temperature remains constant during a phase change. That added heat, that added energy, is going to breaking the bonds that hold that material together. So if we have solid ice, any heat that we add as we melt it is going to breaking the bonds that hold that ice crystal together. So one of the takeaway points that I want you to remember from that graph I showed you is that it takes energy to change the phase of a material. If I want to take a block of ice and melt it, to take it from the solid phase to the liquid phase, I have to pump some energy into it. I have to add some heat to it, in other words. And that's really what latent heat is all about. latent heat is the energy required to change the phase of a system. Now, a very closely related concept is specific latent heat. So specific latent heat is given by capital L, and basically we're just dividing out the mass from the latent heat over here. So in other words, this is the amount of energy that's required to change the phase of 1 kilogram of a substance. So the units for specific latent heat are going to be joules per kilogram, because it's an amount of energy we need to change the phase of 1 kilogram of the substance. So the formula that we have here is Q is equal to plus or minus M times L. So what does this all mean? Q is the heat that's flowing into or out of the system. M is the mass of the substance that's undergoing a phase change. So if we're talking about ice, it would be the mass of the ice. And L is the specific latent heat. That's the specific latent heat of the substance that our system is made out of. And I'm going to show you what the meaning behind this plus or minus sign is, because sometimes this can be positive, other times it can be negative. I'll explain that later. But notice how in this equation, the temperature doesn't come into play. That's because during a phase change, the temperature remains constant. That's another important thing to remember about latent heat, is that when a system is undergoing a phase change and taking in that latent heat, the temperature remains constant. So now let's address the plus or minus sign that we see here in the formula for latent heat. So sometimes the latent heat will be positive, other times it will be negative. So if your system is taking in the latent heat, if it's gaining latent heat, then Q is positive. You're going to use the plus sign. Now this happens whenever your system is melting or evaporating. So if we think about it, if we're going from the solid phase to the liquid phase, we're melting, the system is going to have to take in some heat. Q is going to have to be positive. And by the same token, if we're evaporating, if we're going from the liquid phase to the gas phase, again, the system is going to have to take in some latent heat. So Q is positive over here. On the other hand, if your system is giving off the latent heat, okay, if Q is negative, that's going to happen whenever you're condensing or freezing. So if we go from the gas phase to the liquid phase, that's called condensation. Again, Q is negative because your system is giving off that heat in order to go from gas to liquid. And in a similar way, if your system is freezing, going from liquid to solid, again, Q is going to be negative because your system has to give off heat in order to do that. Okay, so that's how we deal with the sign in the equation. All right, so just to recap and go into a little bit more detail, whenever we have a phase change, so during a phase change, the heat involved in that phase change is given by plus or minus M times L. So you can calculate the heat using this formula. And if we solve for L in this formula, we have L equals plus or minus Q over M. So Q represents, of course, the heat added to the system. And it can be positive or negative, whether heat's coming in or flowing out of the system. M is the mass that undergoes a phase change. And then L is what we call the specific latent heat of the material that our system is made out of. And just so you're aware, sometimes we leave off specific and we just call this the latent heat of the material. Okay? So what would the units be? Of course, well, we have an energy on top. So joules would be the unit, and then we have a mass on the bottom. Kilograms would be the unit down there. Now, I want you to compare this to what happens during a temperature change. So there's no phase change occurring. The heat in that case is given by mc delta T. So basically we have these two formulas. The first one We use that whenever there is a phase change occurring. And we use this other formula when there's no phase change occurring, and all that's happening is the temperature is going up or down. Now, why is there no plus or minus sign in the second equation? Well, basically, the positive or negative sign is accounted for by delta T, because delta T can be positive or negative. Okay, so that allows Q to be positive or negative depending on whether the temperature is going up, in which case it's positive, or if the temperature is going down, in which case it's negative. Okay, so what we're going to start doing is using these two equations together in more complicated problems. So when it comes to latent heat, there are actually two types that we need to be aware of. There's the latent heat of fusion, which is LF, and the latent heat of vaporization, which is LV. Now, as an example, let's think about water once again. Specifically, let's say we have a chunk of ice that is at the melting point to start off. So if we have water in the solid phase, if we have a chunk of ice, this is what you should be thinking of on the microscopic scale. We have a lattice of water molecules, where each water molecule is in a fixed position within the lattice. Now, even though each molecule is in a fixed position, they can still jiggle back and forth. There can still be vibration of the molecules within the lattice, but each molecule has to maintain a fixed position within that lattice. Okay, so if we want to turn this from solid ice to liquid water, what we need to do is overcome the forces that hold this lattice together. So there are forces between the water molecules that keep them in those fixed positions. We need to overcome those forces in order to turn it into liquid water. So the heat that we add to this solid ice is not going into kinetic energy. In other words, we're not increasing the speed at which the molecules are jiggling back and forth, but instead we're changing the potential energy of those molecules as we break the bonds that hold them together in this lattice. So, as we're undergoing this phase change, the temperature stays the same because the kinetic energy of those molecules stays the same. It's the potential energy that's changing as we break these bonds. And so the energy that we have to add to this solid ice in order to make it undergo the phase change, in order to break those bonds, is what we call the latent heat of fusion. So it's the latent heat of fusion when we're going from solid to liquid. And for water, the latent heat of fusion, LF, is 3.34 times 10 to the 5 joules per kilogram. So if you have solid ice at the melting point, for every kilogram you have, it's going to take 3.34 10 to the 5 joules to make it melt. Okay, now there's a very similar thing that goes on when we're at the boiling point. So if we have liquid water, the molecules are no longer in a fixed position. They can move around, but they have to stay relatively close together to be in the liquid phase. But in the gas phase, now the molecules can get really far apart. So in order to undergo this phase transition, we need to add some latent heat. This is called the latent heat of vaporization, going from liquid to gas. So for water, the latent heat of vaporization is 2.26 times 10 to the 6 joules per kilogram. Again, that means if you have a kilogram of liquid water at the boiling point, it's going to take 2.26 times 10 to the 6 joules of energy to get all of that water to evaporate. Okay, that's the idea. Now, with that said, let's do an example problem. How much energy is required to boil away 2.75 kilograms of water, which is initially at 10 degrees Celsius? So there are some numbers we're going to need to use in this calculation. For liquid water, the specific heat is 4,186 joules per kilogram per degree Celsius. And the latent heat of vaporization is LV, 2.26 times 10 to the 6 joules per kilogram. So we're going to ignore any heat flowing to the container. We're just going to imagine that all of this heat is going directly to the water. So pause the video, try to work this out, and then we'll go through it together. Okay, so the total heat that we need to add to the water in order to get it to boil away is going to be in two parts. So we have MC delta T. This is the heat that's needed to get the water, the liquid water, to the boiling point. Which is 100 degrees Celsius. Remember, if it's at 10 degrees Celsius, it's not going to boil. We need to increase the temperature to 100 degrees Celsius before the phase change can even start happening. And then once we're there, we need to add the latent heat of vaporization, so M times LV. This is the heat needed to undergo the phase change. So we need to add both of these together in our calculation. And of course, the phase change is liquid to gas. Okay, so let's plug in what we know. The mass is 2.75 kilograms of water. Lowercase c is the specific heat. That's 4,186 joules per kilogram per degree Celsius. And then delta T is the temperature change. Well, we end up at the boiling point, 100 degrees Celsius, and we start at 10 degrees Celsius. So this is T final, 100 degrees Celsius, and this is T initial, 10 degrees Celsius. So T final minus T initial is delta T. And then again, we're going to add that to 2.75 kilograms, that's the mass, once again, times LV, the latent heat of vaporization, which is 2.26, 10 to the 6th power joules per kilogram. And so if you crunch those numbers, what you're going to get is 7.251 times 10 to the 6 joules, but we'll want to round that to 3 sig figs. So that will be 7.25, 10 to the 6 joules, or equivalently 7.25 megajoules. Remember, M is the prefix for mega, which is 10 to the 6. So that's how much energy you need to add to this water in order to get it all to boil away. So here's another example involving latent heat. So a 50-gram solid ice cube whose temperature is 0 degrees Celsius, so it's at the melting point, is placed in a microwave with a power output of 1,000 watts. So remember, a watt is a joule per second. So how long will it take for the microwave to completely melt the ice cube? We're going to assume that all of the energy that's output by the microwave goes into melting the ice cube. So remember, for water, the latent heat of fusion, LF, is 3.34 times 10 to the 5 joules per kilogram. So let's work this out. So let's start by calculating the heat that's needed to melt the ice cube when it's at 0 degrees Celsius. So because the ice cube is already at the melting point, we don't need to add any heat to increase its temperature. We just need to add heat to undergo the phase change. So the heat is going to be given by Q equals positive M times LF. We know it's positive heat because the ice cube has to take in this energy in order to melt. And M is the mass of the ice cube, so that's going to be 50 grams, which is 50 times 10 to the minus 3 kilograms. LF is the latent heat of fusion, which is 3.34 times 10 to the 5 joules per kilogram. Okay, so that's going to give us an amount of energy or heat in joules, which is 1.67 times 10 to the 4. Okay, so that's how much energy it takes to melt the ice cube. Now, let's also recall the definition of power. So the microwave has a certain power output. What does that mean? Well, basically, power is energy per unit time. Specifically, the power output of the microwave is the energy that it's giving off to the ice cube per unit time. So we can write this symbolically as P equals Q divided by T, because we're assuming all of the energy that's output by the microwave goes into melting the ice cube. So if we rearrange this to solve for T, T is equal to Q divided by P, where Q is the heat that's needed to melt the ice cube, 1.67 times 10 to the 4 joules. And P is the power output of the microwave, which is 1,000 watts, or 1,000 joules per second. So unit-wise, joules cancel out and we just get seconds. And if you calculate this, you'll get 16.7 seconds. So that's how long it will take to melt the ice cube when you put it in the microwave. And that takes us to calorimetry. Now, calorimetry is the experimental study of heat and heat transfer. So for example, if I wanted to take an unknown substance and measure its specific heat, that would fall under calorimetry. So this diagram we see here shows us the basic components of a calorimeter. This is a device that's very commonly used in calorimetry. And here's what it consists of. So we have an outer cup, and then we have an inner cup, okay? And in between the outer cup and the inner cup is just an air gap. So there's nothing but air in between the two cups. Now, in the inner cup, we have some water. And then we also have a thermometer that's being fed into the inner cup and a stirring rod. And to close it all up is a lid on the very top of the calorimeter. So here's what we can do with the calorimeter. We can take a heated sample of a substance and put it into the water, close the lid, and when we do that, we're basically ensuring that no heat is flowing out of the inner calorimeter cup. Because we have air in between the inner cup and the outer cup, and air is a very poor conductor of heat, there's very little heat flowing out of this inner cup. So basically we have the heated sample of a material that we put in here, we have the water, and then we have the inner cup itself. That system is pretty much isolated from its environment. So if we take a heated sample and put it in the water, that's going to change the temperature of the water. And we can measure that temperature change using the thermometer. So depending on how much of a temperature change we get, we can use that data to determine things like the specific heat or the latent heat of a substance. And we're going to use a device just like this in the very last lab of the semester. So we're going to use a calorimeter to measure the specific heat of a substance. So let's do an example involving a calorimeter. So let's say we have a 1.0 kilogram sample of solid mercury, which is at its melting point. So for mercury, the melting point is minus 39 degrees Celsius. So we place that sample in a 0.50 kilogram aluminum calorimeter cup, which is filled with 1.2 kilograms of water, initially at 20 degrees Celsius. So eventually, all of the mercury melts, and the final temperature that everything reaches when everything is in equilibrium is 16.5 degrees Celsius. So using all this data, we're going to find the latent heat of fusion, LF, of mercury in units of kilojoules per kilogram. So some information we're going to need to know. The specific heats of liquid water and aluminum are 4,186 joules per kilogram degrees Celsius for water and 900 for aluminum. We also need to know that the specific heat of liquid mercury is 140 joules per kilogram per degree Celsius. Okay, there's a lot going on here, so let's try to work it all out. So let's start by drawing a picture of what's going on. The calorimeter cup is made out of aluminum, so that's Al, and it's filled with water, H2O. And then what we do is we put this sample of mercury, which is Hg, into the water. And then it melts, and then eventually the entire system we see here reaches thermal equilibrium. Everything has the same final temperature. So let's put a little box around this. And that box is our system. So the system is the mercury, again given by Hg, the aluminum cup, Al, and the water, that's H2O. Now that system is isolated from its environment. And that means it's not exchanging any heat with its environment. Overall, there's no heat flowing into or out of the system. Now, of course, the aluminum, the water, and the mercury are exchanging heat with each other, but there's no heat flowing into or out of the system. So no heat flows in or out of the system. That's how a calorimeter is designed. So when it comes to Q total, we have a number of different terms that need to be added together. So first of all, the aluminum, it undergoes a temperature change. The aluminum is going to cool down a little bit. It goes from 20 degrees Celsius to 16.5 degrees Celsius, in fact. So the heat involved in that is the mass of the aluminum times the specific heat of the aluminum times the temperature change of the aluminum. And by the way, this is going to be something negative because the aluminum is decreasing in its temperature. And then similarly, for the water, we're going to have the mass of the water times the specific heat of the water times the temperature change of the water. And again, the water cools off, so that's going to be a negative heat for the water. But then for the mercury, a couple things happen. First, the mercury melts. So it has a positive latent heat term, which is M for the mercury times the latent heat of fusion for the mercury. So this is the heat required to melt the mercury. But after it melts, it still takes in more heat in order to get to the final temperature of the system. So that's going to be given by mass of the mercury times the specific heat of the mercury times the temperature change of the mercury. Again, this is to bring the mercury to the final temperature. Okay? And both of these are going to be positive, by the way. So we have positive latent heat and also positive heat as the mercury increases its temperature and everything reaches equilibrium. So all of these four terms, when we add them together, two of them are positive, two of them are negative, so they can add up to 0. Okay, so now let's put some actual numbers into that expression that I wrote down. So starting with the mass of the aluminum. The mass of the aluminum is 0.5 kilograms. The specific heat of the aluminum is 900 joules per kilogram per degree Celsius. And then the temperature change of the aluminum is this. We have T final minus T initial. So that's going to be T final 16.5 degrees Celsius minus T initial, which is 20 degrees Celsius. Okay, so the aluminum starts off at 20 degrees Celsius. So that's T initial right here. And then it ends up, like everything else, at a final temperature of 16.5 degrees Celsius. Okay, then for the water, we have the mass. The mass of the water is 1.2 kilograms. Specific heat, 4,186 joules per kilogram per degree Celsius. And the temperature change is the same. The water ends up at 16.5 degrees Celsius, that's T final. Starting off at 20 degrees Celsius, that's T initial. Okay, next, we have the mass of the mercury, which is 1 kilogram, 1.0 kilograms. The latent heat is what we're trying to find, so we'll leave that as an unknown. And then we have in our final term, the mass of the mercury, which is 1.0 kilograms. The specific heat of the mercury is 140 joules per kilogram per degree Celsius. And then the temperature change for the mercury is different. So T final is 16.5 degrees Celsius because everything reaches the same final temperature. But for the mercury, the initial temperature is actually minus 39 degrees Celsius. That's T initial for the mercury. So all of that is equal to 0. All right, so if you crunch the numbers, the very first term comes out to minus 1,575 joules. If you look at the units, kilograms cancel, degrees Celsius cancel, so we're just left with units of joules. For the second term, works out to minus 17,581 joules. The third term is just 1.0 kilograms times LF, which we still don't know what the value is. We'll figure it out. And then the last term, if you crunch the numbers, is 7,770 joules. So all of that is equal to 0. So basically, to simplify this, we have 1.0 kilograms times LF. If we combine all of the other terms on the other side of the equation, it works out to 11,386 joules. So the latent heat that we're trying to find is just 11,386 joules divided by 1 kilogram, which is 11,386 joules per kilogram. But we want to keep 2 sig figs on that. And here, let's do a unit conversion as well. In every 1 kilojoule, we have 1,000 joules. So we divide by 1,000. That's going to be 11.386 kilojoules per kilogram. And then if we round it to 2 sig figs, it's about 11 kilojoules per kilogram. So if you have mercury that is right at the melting point, it takes about 11 kilojoules of energy to get a kilogram of that mercury to melt. That's what we found here. So let's check out another example. Here we have a 0.5 kilogram chunk of ice, which is initially at negative 10 degrees Celsius. We take that chunk of ice and we place it in 3 kilograms of water, and that water is initially at 20 degrees Celsius. So the question is, will all of the ice melt? Yes or no? And then also, what will the final temperature of this system be? So when the ice and water reach equilibrium, what is that final temperature? We're going to consider the ice and the liquid water to be an isolated system. So that means we're going to ignore any heat flowing into the environment, which includes the container that holds the water. Okay, so between the ice and the liquid water, that is an isolated system. So if we're trying to figure out whether or not all of the ice will melt, the question we're really asking here is, what is the final phase of the system? There are 3 possibilities, and let's outline them here. So one possibility is that the final temperature ends up being something less than or equal to 0 degrees Celsius, and it's all solid ice at the end. So in other words, you put the ice cube in the water, and that freezes all of the water, so it's all solid. Another possibility is that it's all liquid, and the final temperature is above or equal to 0 degrees Celsius. So that means you put the ice in the water and the water melts all of the ice and it's all liquid at the end. And then the third possibility is that you have some kind of mixture of liquid and solid. And that can only happen if the temperature is exactly 0 degrees Celsius. So it's possible that at the end of this process, once the equilibrium is reached, you have some mixture of liquid water and solid ice. These are the three possibilities, and we're going to test each one of them out to see which one is correct. As we test out these possibilities, we're going to have to keep in mind two really important facts. So the first is the ice and the water are going to reach the same equilibrium temperature. So it's the same T final. That's what it means to reach equilibrium. Everything is at the same final temperature. Also, the water and the ice constitute an isolated system. So that means Q ice plus Q water is equal to 0. Any energy lost by the water is gained by the ice. That's how you interpret this equation. Okay? So let's start by testing out possibility number 1, which is that at the end of this process, it's all solid ice. That means all of the original liquid water is going to have to freeze. If it's going to freeze, it's going to have to give off a bunch of heat. So what is the heat that the water will have to give off in order for all of it to freeze? Well, we first need to have the water give off some heat in order to reduce its temperature to the freezing point, 0 degrees Celsius. So that's going to be the mass of the water, 3 kilograms, times the specific heat of liquid water, 4,186 joules per kilogram per degree Celsius, and then delta T, the temperature change, is 0 degrees Celsius for the final, minus 20 degrees Celsius for the initial. This is the heat the water gives off to get to 0 degrees Celsius, to get to the freezing point. But then, in addition to that, it's going to have to give off some latent heat in order to change phase, in order to go from liquid to solid. And that's given by negative, because we're freezing, this is going to have a negative sign. The mass, 3 kilograms times the latent heat of fusion, 3.34 times 10 to the 5 joules per kilogram. So if we crunch those numbers, it works out to minus 1.25 times 10 to the 6 joules. The water is going to have to give off this much heat for all of it to freeze. But at the same time, the original ice can't melt, right? So we don't want any of the ice to melt. So the most heat that the ice can gain without any of it melting is equal to this. We have the mass times the specific heat of ice times the delta T for the ice. So here, let's see what we have. So the mass of the ice is 0.5 kilograms. The specific heat of solid ice is 2100 joules per kilogram per degree Celsius. And the most we can increase the temperature of the ice by is up to 0 degrees Celsius, because if we go past that, then it's going to start melting. So we can just get right up to the melting point, and that's as far as we can go. So the final temperature is 0 degrees Celsius minus the initial for the ice, which is negative 10 degrees Celsius. If you crunch those numbers, it only comes out to 1.05 times 10 to the 4 joules. So possibility number 1 is not going to work, because if you think about it, the water is going to have to give off this much heat, and the ice is going to have to take all of that heat in. But it can only take in this much heat, a much smaller amount, 10 to the 4 joules, if none of it is going to melt. So to freeze all the water would have to give off more heat than the ice would be able to gain without any of it melting. So it's just not possible that in the final state, everything is solid ice, okay? This just can't happen. Okay, the energy balance doesn't work out. So let's also test out possibility number 2, which is that all of the ice melts, and in the final state, it's all liquid water. So if all of the ice is going to melt, it's going to have to take in some heat. It's going to have to gain some heat. Let's calculate what that would have to be. So the heat that the ice would have to gain is equal to a couple different things added together. The first term is this. We need to get the ice to the melting point. So the heat that we need to add to the ice to just get it to the melting point, to get it from negative 10 degrees Celsius to 0 degrees Celsius, is the mass, which is 0.5 kilograms, times the specific heat of solid ice, which is 2100 joules per kilogram per degree Celsius, and then times 0 degrees Celsius, that's the final temperature, minus negative 10 degrees Celsius, which is the initial temperature. That gets us to the melting point. But then we have to melt all the ice. We have to change phase. So that's going to be a positive latent heat because we're melting. And it's going to be equal to 0.5 kilograms times the latent heat of fusion, 3.34, 10 to the 5 joules per kilogram. So it's going to need to gain at least this much heat, which is 1.78, 10 to the 5 joules. Okay, that will melt all the ice. Now, we don't want any of the water to freeze because we're imagining in the final state it's all liquid. So how much heat can the water give off without any of it freezing? That's the question we'll ask here. So basically, if we take the water from 20 degrees Celsius all the way down to 0 degrees Celsius, right at the freezing point, it can give off that much heat and none of it will freeze, okay? So we can calculate that heat. It's the mass of the water, which is 3 kilograms, times the specific heat of liquid water, which is 4,186 joules per kilogram degrees Celsius. And then delta T, the temperature change, is 0 degrees Celsius for final, minus 20 degrees Celsius for the initial, which works out to 2.51, 10 to the 5 joules. And there's actually a typo here. This should be a negative sign because the water is giving off this heat, okay? But the point is, the water has more than enough energy that it can give off to melt all of the ice. So the final state is number 2. It's all liquid water with a final temperature something above 0 degrees Celsius, something above the melting point of water. So now what we're going to do is find the final temperature. Since we know the final state is everything is liquid water, let's find the final temperature. So what we'll use here is the heat that's gained by the ice plus the heat that is lost by the water equals 0 because, again, we're assuming the ice and the water are perfectly isolated from the environment. So here's what we'll do. For the ice, we need to get it to the melting point. So the heat is the mass of the ice times the specific heat of the ice times the temperature change, which is 0 degrees Celsius for the melting point, minus the initial temperature of the ice, which I'll call T0I. Okay, then we're going to melt all of the ice. So the heat that goes into the ice is the mass of the ice times the latent heat of fusion, LF, for the ice. But then we have an additional term. The melted ice, which is at 0 degrees Celsius, increases its temperature to some T final. Whatever the final temperature is, it's above 0 degrees Celsius. So we have the mass of the ice now times the specific heat of liquid water because it's melted, it's in the liquid phase. And then we'll have T final minus 0 degrees Celsius. That gets the melted ice to the final temperature. So this is all part of QI. For the water, we have the mass of the water times the specific heat of water times our T final, which we'll figure out, minus the initial temperature of the water, okay? This is QW. This gets our water from the initial temperature to the final temperature. And when we add all of that together, we get 0. So we'll put the numbers in. For the mass of the ice, we have 50 kilograms. For the specific heat, we have 2100 joules per kilogram degrees Celsius. And then we have 0 minus negative 10 degrees Celsius because that's the starting temperature for the ice. And then in the next term, we have the mass of the ice, which is 0.5 kilograms, times the latent heat of fusion, which is 3.34 times 10 to the 5 joules per kilogram. And then in this term, we have 0.5 kilograms times, now we have liquid water, which has a specific heat of 4,186 joules per kilogram per degree Celsius. And then we don't know what T final is, so we're leaving that as a variable. T final minus 0 degrees Celsius. Then, in the last term, we have the mass of the water, 3 kilograms times specific heat of water, 4,186 joules per kilogram per degree Celsius. And then we have T final, again, we don't know what that is, minus 20 degrees Celsius for the initial temperature of the water. So it took some time to set up this equation, but now it's pretty straightforward. It's a single equation with a single unknown variable, which is TF. So I'm going to skip over the algebra that you would go through to solve this equation, but when you solve for T final, you'll get 5 degrees Celsius. So the final temperature is 5 degrees Celsius. It's all liquid water. That's how you do this one. So let's take a look at one more example. Let's say we have a 146 gram copper bowl, which contains 223 grams of water. Initially, both the bowl and the water are at 21 degrees Celsius. A very hot 314 gram copper cylinder is dropped into the bowl, and that it's actually so hot that it causes some of the water to boil away. It boils away 4.70 grams of water, and it converts it into steam. So the question is, what was the initial temperature of that copper cylinder? So in order to figure this out, we'll have some specific heats. We have the specific heat of copper, which is 387, and water, which is 4,186 joules per kilogram degree Celsius. We also need to know that the latent heat of vaporization of water is 2.26 times 10 to the 6 joules per kilogram. So we have the bowl, we have the water, and we have the cylinder. We're going to consider that to be an isolated system as we calculate the answer. All right, so let's go through this one. Okay, so we'll start by drawing a picture. Here's the bowl. It's filled with water. And then we place the copper cylinder into the bowl like this. So this is our system. So the system is the copper bowl. And by the way, the chemical symbol for copper is Cu, so I'm going to be using that. Copper bowl, copper cylinder, okay, and then also the water, the H2O. Okay, now the system is isolated from its environment. And so what that means is Q total is equal to 0. So there's no heat flowing in or out of the system. So of course, the different parts of the system, the bowl, the copper cylinder, and the water, will exchange heat with each other, but they're not going to be exchanging heat with the environment. Okay, so what is T final? We should get a sense of that. Well, first of all, T final will be the same for all parts of the system because they reach equilibrium, but we know that some of the water has boiled away, and that can only happen at one temperature, which is 100 degrees Celsius. We know this since water is being converted to steam. And again, it's that same final temperature for all parts. Okay, so with that said, let's figure out a way to expand this equation out and write down what are all the different parts that go into Q total. Well, the bowl is going to heat up. It's going to increase its temperature. So we have the mass of the bowl times the specific heat of copper, that's what the bowl is made out of, times the temperature change. Okay, so that's a positive amount of heat for the bowl. We also have the cylinder, okay? The cylinder has a mass, which I'll call M cylinder. It's made of copper, so the specific heat is actually the same. And the temperature change of the cylinder goes here. Now the cylinder starts off really, really hot, and then it cools off. So this will be a negative heat for the cylinder. Now for the water, here's how we have this. We have the water needs to heat up to the boiling point. So we have the mass of the water times the specific heat of water times the temperature change. And specifically, this is to get the water to the boiling point. But there's also another heat term which accounts for the fact that some of the water boils away. So we have another heat term that accounts for the fact that some of the water boils away. And that's going to be a mass times a latent heat for vaporization. But it's not the same mass that I said over here, right? It's not like all of the water boils away, only some of it does. So let's call this MV for the mass that vaporizes. And then once we do that, we can set this whole thing equal to 0. Okay, now let's put the numbers in. So starting from the very beginning of the equation, we have the mass of the bowl, which is 146 grams, or 0.146 kilograms. All right, and then we'll take that times the specific heat of copper, which is 387 joules per kilogram degree Celsius. Okay, what's the temperature change of the copper bowl? Well, it ends up at 100 degrees Celsius, so that's T final. And then we subtract T initial, which is 21 degrees Celsius. Okay, so that's the first term for the copper bowl. Now, for the copper cylinder, the cylinder has a mass of 314 grams, which is 0.314 kilograms. It's also made out of copper, so we use the same specific heat, 387 joules per kilogram degree Celsius. Now, what's the temperature change of the cylinder? Well, T final is 100 degrees Celsius, like everything else in the system. But T initial, we don't know. So I'm actually going to leave that as a variable. So this is the initial temperature of the cylinder. We don't know what that is, so it's a variable T initial. Okay, next. We have the mass of the water, which is 223 grams, or 0.223 kilograms, times the specific heat of liquid water, which is 4,186 joules per kilogram degree Celsius. And the water ends up at 100 degrees Celsius, starting off at 21.0 degrees Celsius. So that's our delta T, 100 minus 21 degrees Celsius. And then finally, we have the mass of the water that actually vaporizes, which is only 4.7 grams, or 4.7 10 to the minus 3 kilograms. So we're not using the whole mass of the water, just this portion of it that actually vaporized. And then we multiply that by the latent heat of vaporization, 2.26 10 to the 6 joules per kilogram. And that all equals 0. So again, it's pretty straightforward to calculate the result from here. We just have a single equation with a single unknown, which is T initial. We want to find out what that is. So here, the first term, if you crunch all these numbers, first of all, the units of kilograms cancel and the degrees Celsius units also cancel. So we're just left with joules. It's 4,464 joules. Okay, for the second term, we want to split it up into two parts. We have 0.314 times 387 times 100. That works out to positive 12,152 joules. And then what we're going to do is look at the second term, which is 0.314 times 387 times minus T initial. So this is going to be minus 121.52. The units are joules per degree Celsius here, multiplying T initial. Okay, then we have this entire term right here, which if you crunch the numbers is 73,745 joules. And then this entire term is 10,000, oops, what just happened? 10,622 joules. So that all equals 0. So basically, combine all the constant terms into one. So add this to this to this to this. You'll find that it works out to 100,983 joules. And then we'll take the negative term and add it so it's positive. On the other side of the equation, 121.52 joules per degree Celsius times T initial. Solve for T initial. That's 100,983 joules divided by 121.52 joules per degree Celsius. So if you work that out, it comes out to 830.99. We're going to actually keep 3 sig figs on this, degrees Celsius. So about 831 degrees Celsius. So that was the initial temperature of the copper cylinder that we put in the water and caused it to boil away some of that water. Okay, that's what we found here. So that's going to be it for this video. We're going to finish up this lecture in the next one, so I'll see you then. But until then, as always, hope you're doing well out there. Be safe, be healthy. See you later.